Afternoon, everyone. I've gotten green light of the leader of the room here. Welcome, everyone. Thanks for the invitation to Berco. My name is Onno Zoeter. I currently head up Booking AI research. I did my PhD from 2000 to 2005, so I'm exactly a week and a month off from being 25 years full-time working on AI. Worked at Microsoft Research, Xerox Research, and about 10 years ago I was asked to come and head up machine learning company-wide at Booking. And I did that for 4 or 5 years, and after that went back to my passion of research and started and now lead Booking AI research. And looking over the program of this event, I thought, okay, how to best use the time that we have together. I thought, let me have 2 parts to this talk. So the first part will be on the lessons that I've learned setting up and leading machine learning company-wide, and the teaser of some of the lessons learned there. Second half is an example and a motivation of why does Booking have a research lab and what type of things can you expect from that. Right? That's the more technical part. So, first part, how should you organize yourself for success? I don't think, actually I'm quite sure, given that you all are here, I don't need to convince you that AI is a real thing, that there's a lot of substance under all the hype. You know, some of it is overhyped, but it's a real thing, will really impact the world. But it's actually not the first breakthrough. There have been several. Who recognizes this plot? Who knows ImageNet? Very good. So this is the ImageNet result graph. Horizontal axis is the years. Every year there was the ImageNet competition. Who could predict or classify image categories the best? All academic and industry labs would compete. And it's a little bit unfortunate, so this is from the Electronic Freedom Foundation, this plot. If we would have more data to the left, you could see the plateau that was there. My previous job was Xerox Research Center Europe, who had won in 2011. And when my colleagues from the computer vision team came back from the conference in 2012, they had their jaw on the floor. Every little progress in the years before was super hard fought, and no one had guessed and expected that you could make such a jump. Yeah, so that's the deep neural net moment in 2012. It's a good reminder that it's not the first breakthrough, and if you are part of a bigger company, or you're consulting for bigger companies, that actually a lot of gains are there still in the pre-gen AI part of AI, right? So to give you an idea of what the big applications are at Booking, Booking spends billions a year on online advertisements. So the systems that predict, will this customer in this context click on an ad, and then will it buy something, and how much will that customer spend, are key ingredients to bid optimally. And that's in an environment where we are in direct competition for customers with our direct competitors, right? Super important. We spent in the order of $1 billion on discounts, and to make that a good investment, we need machine learning models to predict when that is critical. We accept hundreds of millions of payments a year, and that is only possible because we can good enough predict fraud and prevent that. We translate reviews, we rate, we rank, and we recommend, and so on and so forth. And so these are all essential components in the business. So when I joined, there were the first tentative users of machine learning, and within 4 years, it was a very robust distributed setup with machine learning essential in all parts of the business. And these were all techniques pre-Gen AI. Right? So now, of course, we're trying to figure out where and how can we use Gen AI the best. But it's good to keep in mind for all of you, there's probably many companies still lots to gain from the earlier hype. This is an image that we use quite a lot at Booking. On the left, you see a classic organization of a company, where you have the CEO at the top with a bright idea, and then several layers of management translating that down to teams that build something, and then it's kind of a take it or leave it to customers. Sometimes this is necessary. If you need to decide to build a humongous battery factory in Nevada, maybe you're forced to work this way. In digital products, you can invert that pyramid. So you can empower teams to experiment and to listen directly to customers, to have each team come up with a bright idea and have them be at the top and driving things. You need less management layers, and they're effectively only there to support that democratized way of innovating, right? In the face of Gen AI, where lots of things might be candidates for success, if you limit the ID generation to a small group of people, you risk missing some, right? So if you can, it's extremely powerful to democratize and to empower every individual in your organization to help and innovate and think of what customers might want next. That's at least the theory. And the theory is very strong. So I think if you are in a business where you can A/B test and you don't, you're at risk, right? But the theory says it's blue skies, beautiful conditions, one foot in front of the other, you're steadily increasing, always better. But in practice, there are many, many things that you didn't think of when you were making all the plans that make it a lot harder in practice. So to execute this thing, you need to be paranoid. Because before you know it, things are very dire, freezing, and you just are happy to get back alive in the hut. So much for excuses to show you my holiday pictures. Let's take it back to what does it mean? It's very easy to make a first demo, to have a proof of concept, to have a prototype. This was already the case with the previous generation of AI. It's now even more so. You can cook up something that looks quite fancy to people not yet knowing the power of Gen AI in a matter of days, if not a day. Making something that really solves a customer problem, that they really enjoy and come back to, that's very hard. Building a system that outperforms your heuristics that you've iterated and improved over years, that is very, very hard. Who recognizes this? Okay, if you don't, you're probably not testing rigorously enough. And it's one of the most important things for you to get right. Because the chances that your first idea and the first execution of that idea is the right thing is very, very small, right? If people come to you and they explain their success, and it doesn't come with all the war stories of all the things that went wrong along the way that they had to overcome, the chances that that is a real success is very, very, very small. Yeah. So the reliable experimentation is key. It looks like a very innocent phrase, but if you go this route, and in fact anything that you want to now also try out with Gen AI, what might work, be paranoid on how to detect if the thing that you're trying is not really what you should, and you should make a tack and do something slightly different. Yeah. And that is, so for the younger folks in the audience, it's not just booking, but try and find a place where you can get honest feedback on the stuff that you're building. Yeah? So that with customer base that can give you feedback on your ideas. If you're building a prototype in the attic, it's nice, but you won't get expert as quickly as you can if you are in an environment where you can get end-to-end feedback. Many other things. How close can you operate to state of the art and so on? Maybe one thing that struck me, there's a long list of very fun and important lessons I learned along the way. One thing that came back time and time again is that you come in and you think getting the technology right will be the hardest thing. And it is essential, of course. It's very fun. If you come with a tech background, that's what you gravitate towards. Most of the things of getting from failure to success, a lot of it had to do with incentives. So let me give you a hypothetical example. I'll make something up. So you're in a company, and you look along and you see email marketing messages going out. Yeah? And you see that they look like a lot, right? It smells even a bit like spam. So you go and you look, you go and sit with the team. So what might be up, right? Maybe these people don't know that you can build models to predict relevance, right? Or so maybe the know-how isn't there. Or maybe the know-how is there, but they can't build the models, or they don't have the data to train the models, right? Or they are not allowed to experiment, right? And so you go and the team is there, the tools are there, you see them building models, so it's not a limitation of the infrastructure, and they are allowed, to this inverted pyramid idea, they can experiment, right? So they are allowed to take every so often a batch of email addresses in A, a batch of email addresses in B. They say, do whatever you want, and we will score you how many free sales do you get in the batch of emails that you've been assigned. And if you can get more in your version B than there was in the old version A, then that's counted as a win. Yeah? Because we don't need to pay. We don't need to pay money to Google to get these customers in. It's just free sales. Yet, under all these seemingly ideal conditions, blue sky, great conditions, there's still the outcome that there are too many emails sent. It's your gut feeling. So what's up here? Is that maybe your gut feeling is wrong? So maybe it's business optimal to send this many emails? Or is there something else wrong? Anybody wants to venture a guess? Shy room? No? Okay, of course you guessed right, but you didn't say it out loud. It's of course in incentives. So what is offered the incentives? The teams are scored. How many free sales? How many sales do you get out of this batch of email addresses that you can send emails to? Right. So if you think, well, I have a machine learning model that can predict that this half of these email addresses have next to zero interest in this email. It would just be nuisance and noise to them. And you decide not to send to half your email base this email. According to the metric, you just have a strictly lower expected number of sales that you're getting. Right? So because of your metric, there's absolutely zero incentive to send less emails. And so the seemingly innocent, quite reasonable metric is what prevents these teams from doing what ultimately is the right thing for the company. And when you first talk to this team, they might not even be self-aware anymore of this, because this was years ago and they've been doing this all along. And they even forget to tell you that this is what is holding them back. Just one example, and there are many, many, many. Just give me a few beers and we can go through very many. To give you a taster of what it feels like to set up such a machine learning organization at scale. Then research. So I told you a little bit about some applications at Booking. We have more than 100 people with the title machine learning scientist. We have machine learning engineers, and we have product people that know a lot about machine learning. It's a large group of people by now. And Booking, I research and say, well, we can add 5 more or 10 more, 20 more people to this batch that we already have. We're going to run an experiment. What if we can tap into the type of expertise that we currently find difficult to recruit? So the people that can be full professor at the top university and are very in-depth in particular niches that we think are important to the company. So I want to give you one example of what that looks like. So first off, Booking I Research, we organize ourselves in labs. So at the moment we have 3 with University of Amsterdam and Delft and Northwestern and CWI. I want to focus on the first theme of the first one, where we combine causality, information retrieval, and reinforcement learning in something that we call, for now, learning from controlled sources. What does that mean? Who of you know supervised learning? Good. That should be, machine supervised learning is, rightfully so, the workhorse of AI. It is what is covering most your first courses in machine learning. It is what is the biggest bulk of the textbooks. However, when you apply models, so you don't just build the models to pass your course or to win a Kaggle competition, you're actually going to use them, then very quickly the problem that you find out that you need to solve is richer than just a supervised learning problem. Right? So your data, might be biased because some aspects of your data have been filtered out. We'll see an example in a bit. Or your data represents a natural phenomenon that you try to model, but it is a combination of an old controller that tries to get the most out of that natural phenomenon. So you need to disentangle what is what. Or because you build your model and launch it, say it's an alarm or so, the world will start behaving differently. And so you need to anticipate that and play optimally and plan for that optimally. We don't pretend that we have a full list of all these things and all these ways in which it can extend beyond supervised learning, but the practice is that when you actually use these things in practice, it very quickly is richer than just that. And there are no standard tools that you can tap into that solve that for you. Yeah, so the idea is we're going to try and work through these and add that to the standard toolbox of teams. To give you an idea, this is supervised learning. So say the inputs, the RGB values of 100 by 100 image, that's X, and then Y, is it a cat or a dog, right? And we're going to learn the model P of Y given X. Now this one. So we changed what Y means. It's not cat or dog, it's fraud or a valid payment. And X is not the RGB values, it's just everything we can get our hands on at decision time. When we need to decide, do we accept this payment, yes or no? Right, so we're going to build this model again, predict probability of fraud, given what we can measure, P of Y given X. And now we're going to use it. So if that risk of fraud is too high, we're going to reject the payment. So the selection S of X is 1 if the probability of fraud is sufficiently low, otherwise it's 0. Now, out of this context, you might say, okay, well, this is just binary classification again, just like cats and dogs, right? And there are plenty of tools that we can get off the shelf to try and solve this. But I'm claiming there's something fundamentally missing here. Anyone want to venture a guess? So it's imbalance in the sense that there's way more non-fraud than fraud, right? Yeah, fair enough. That's going on. It's not what I'm hinting at here. There are yeah, so maybe you can't use some of the features, you know, we don't want to protected group. That might also be going on, but that's not what I'm going.
Like when you're optimizing for?
So how we set tau is a function of the business numbers of what does the fraud cost us and what do we gain from a regular customer. True, that's also going on. Right. You have a prior, but if that's a prior over Y, once we, in which way or other, if we get P of Y given X, then that should have come in the right way. Survivorship bias, yeah. And so in what sense exactly?
So you don't know when you don't know. So if you say that something is a fraud and you don't let it, you might not know. Or if you approve only if you approve something you shouldn't, then you know.
Yep.
You got it correctly.
Yep. Yep. So this was the thing I was after. So what is fundamentally different from the cat-dog example? And if you think about it, the cat-dog example is also in machine translation, speech recognition. Many of the early big important successes, surprisingly, or maybe because of that, none of those canonical examples suffer from this, what I know, this effect of learning from controlled sources. So that you would see in e-commerce or in health applications or in other. But here we see, so this selection variable is 1, if we accepted the payment, then we learn the label. Was it fraud? 1, or was it not? 0. If we don't, then it remains a question mark. And I'm going to claim this data set is biased. So for instance, consider if we ask ourselves, of all the payment requests that we get, what fraction is fraudulent? And we would compute that naively as the ratio of the green entries in this last column. Then will we be wildly optimistic? Because if our system that was filtering things out was somehow decent, it has filtered out the obvious fraud cases. So the ratio of fraud to not fraud should be a lot nicer to us in the green rows than in all the rows. Yeah? So it's not missing at random. It's missing because there was a system that was reasonably decent. But now the question is, we want to learn P of y given x. So imagine you have your old system, P of y given x, and you have now a year's worth more of data. Can you use that year of data to improve your model? So let me give you a multiple choice. So choice A is, don't worry, just add the data to the mix, it will be all fine. Option B is, no, you need to actually do quite some sophisticated reasoning and add correction factors to be able to leverage this new data. Or C, you fundamentally cannot use this data, and you should not. If you want to improve it, you should actively go and fetch new data. So, hands, who votes for A? Just take the data. Who B? Who says, no, you need to be clever, you need to correct for things. Who says C? You just fundamentally cannot. Okay. Who doesn't like raising their hands? Yeah, so is the question. So I always start this thing with this multiple choice question, because if you know of base nets and I will tell you the answer, the risk is that you say, this is obvious. And so it's just also for my own confirmation that the majority answer is never right. And in fact, it's quite often happens that there's no correct answer, but here there was. Do you know why? You quickly.
It's always better to start with just only data and then see how it behaves.
Okay, you were just positive mindset. Okay, but no formal reasoning of why that wouldn't matter. Okay, well, sometimes luck is also a good thing. Let me tell you why. So I set it up here. So the old system was filtering out and it was listening only to X. The X's that we also store in our database and the same X that we plan to use for our new system. Right? So this is the canonical example if we have an old system and we just want to fine tune it. Who knows base nets? Okay, so then for those of you, you will quickly see the answer. For the rest, I will give you a feel for this, so that if you ever hit this type of thing, you know what to read up on. So you can read these graphs as a data generation pseudocode. So in the world on the left, we first generate X. So what is the IP address of the person? What is the time delay sending things back? How often has been this credit card used in the last few minutes? And so that we generate first, and given that, we can generate fraud or not. Probably it's a biased coin then. And S is the decision, do we accept the payment, yes or no? The second world, we first generate fraud, then we generate the signals. In the third world, there's a common cause, maybe the intent to defraud the system, that influences both X and Y. What is important though, no matter what world and how this really comes about that we're unsure about, what we are sure about is that this decision to accept or reject a payment, we know where in this chain of events this happens, and we know that it is an algorithm that is listening only to X. Right? So that causal effect we know. And now if you know BaseNet, then you can reason conditional independencies. So if we know X, which we do know at the time we need to make a decision, Y and S are conditionally independent. What does that mean? P of Y given X and S is the same, it's conditionally independent of S, so it's the same as P of Y given X. So we have our filter data, but despite that filtering, it gives an accurate description of this conditional relationship. If you ever find something like this, then the entry point is S recoverability from Judah Perl. It's first. To give you, for the coders among you, to give you an idea, this is, let me quickly check how much time I have left. Let me go a little bit faster. You can have a coding intuition of why this is so. Come and find me if you're interested. Okay, you might think, oh, well, that's kind of cheating. You try to convince me that there was a problem, and then you say, nah, actually, there's no problem. You can just, that's no fun. There can very easily be a problem. And when can there be problems? Is if you have this filtering happening not just based on X, the thing that you've managed to record and that you will use yourself, but on more. Right? So then there are things that you would interpret as being random, but it's not random. It is carefully chosen. And then you will get a critical bias. And there are cases when you can correct for that. So there are cases when answer B would be the right one. And this is, again, if you ever find these things, the S-recoverability paper will point you out. You can come and hit me up. I'll try and explain. The hardest scenario is if the selection is a direct function of what you're trying to predict. The canonical example is MBA. You've spent a fortune on expensive MBA. You get a survey. Did your salary go up? If your salary indeed went up, you're very proud and you're more likely to send back the survey. In this case, you need to have some other data to find out how strong that bias is. In the real world, it gets a lot more complicated. We hit indeed this complicated scenario. And one interesting thing that we found is that in many cases when people talk about causality for biological processes, for the economy and things like that, it's always a little bit, yeah, sounds complicated and how accurate are your methods? What's surprising is that in a pure software environment, there is a piece of code. You might not have accurate knowledge of which version of the model was running at that time when the data was generated, but you know the journey and the process and what it was looking at. So it's not trivial, but it is possible to come up with such a full model. Which we did, and we applied, and we got way more training data and debiased it, which led to very nice savings and lowest fraud ratio amongst our accepted payment ever. So that's we're very proud. And it's a very nice thing of saying, okay, these problems might occur. We found the interesting theory. And yeah, but it also goes the other way around. So there is theory out there that you can sometimes use on the more advanced problems in your world. There are also things where the theory is not sufficient. So the theory was valid for infinite data, so identifiability results. But we had, of course, finite data. And so we developed methods for that and published that at UAI. So it's nice to introduce you to my collaborators here. It's Philip Boeke, he's a PhD student in our lab, who worked on this. The algorithm that he used here is an extension of what his colleague at the university did, Nout Kroon. Matthijs de Jong is a colleague at Booking who was responsible for this fraud detection model. And Joris is my collaborator professor in the mathematics department in Amsterdam. If you want to know more about causality, it's fun. Brady Neal's course is the best bang for your buck if you want to start. And let me leave it at that so that there's time for questions.